Hey guys, this is section 8.2 and we're also going to do section 8.3 because it's really short. We're going to talk about pressure, temperature, phase diagrams and the phase rule. Let's just start out with a generic pressure versus temperature phase diagram. In here we also have information about which phase the substance is in at a given combination of pressure and temperature. These are made from experimental data. We're getting our algorithms and our computers to the point where eventually we'll be able to calculate these, but at this point it's pretty much done experimentally. Get the data and make the graph. So a couple things about these. These lines that separate the different phases are called coexistence curves or coexistence lines, and at any combination of pressure and temperature that falls on one of these lines, there's an equilibrium between the two phases. So for example, this is the green here is a solid, the blue is a liquid. This black line, the yellow line is something else, we'll do that in a minute. The black line here is a coexistence curve. And right on that line, the solid and the liquid are in equilibrium, which means the chemical potential of the solid phase is equal to the chemical potential of the liquid phase at that point along that curve. Most substances, the molar volume of the liquid is greater than the molar volume of the solid. And when that's the case, this coexistence line here that separates the solid from the liquid phase has a positive slope. It leans to the right. For the weird substances such as water, where the molar volume of the liquid is less than the molar volume of the solid, this line leans to the left. It has a negative slope. And so what that means is, okay, so here's how we read these diagrams. Pick some combination of pressure and temperature. Let's say we start out down here somewhere. So it's a gas at this temperature and this pressure. It doesn't matter what it is. And then if we keep the temperature the same and we increase the pressure, what happens is it goes to a solid. As we keep increasing the pressure, though, with this negative slope, at one point we'll cross this line, and over here would be a liquid phase for this substance, and it would actually, at higher pressures, would become a liquid. You can do this with a block of ice. Water is like this. If you take a really thin wire and hang weights and drape it over a block of ice, put weights on the end, it'll go right through and it'll cover itself back up. Actually, it goes through. It's kind of cool to watch. On the other hand, if it's a normal substance where we have this positive slope for the solid liquid coexistence curve, if we start down here, keeping the temperature the same, this is the yellow line right here. This is an isothermal line. So we go through up here, so the gas becomes liquid as we increase the pressure at the same temperature, and then eventually we cross this line and the liquid becomes a solid at that same temperature. Now, each of these parts of the curve, the solid, gas, so by the way, going from the solid phase here, at this pressure, we're down here, like we start at B, as we increase the temperature at the same pressure, we'll go directly from the solid to the gas phase. That's called sublimation. On the other hand, if we start at this pressure, we increase the temperature, we'll go from the solid to the liquid phase, and then eventually to the gas phase. Each portion of the curve, ends sort of differently. The coexistence curve that separates the solid from the gas phase stops right here. This point right here is called the triple point, because right here at this point there are three phases. It's kind of cool, all in equilibrium: the solid, liquid, and gas. This line here that separates the solid from the liquid phase, that extends up indefinitely. This portion of the curve that separates the liquid from the gas phase, that gas-liquid coexistence curve, ends right here. At this point, this is called the critical point. At any combination of pressure and temperature past this point, we have what's called a supercritical fluid. And what happens is, as you start going along this curve, the density of the gas increases, the density of the liquid decreases until they become the same up here as a supercritical fluid. at the triple point right here, the change in enthalpy of sublimation going from the solid to the gas is equal to the sum of the change in enthalpy of fusion, melting, plus the change in enthalpy of vaporization going from a liquid to a gas. And actually, as a practical matter, anywhere reasonably close to the triple point, that is also true. Delta H of sublimation equals delta H of fusion plus delta H of vaporization. But as you get farther and farther away from the triple point, you have to take into account the temperature dependence of the heat capacity of the different substances, as well as the temperature dependence of the heat of transition, heat of fusion, heat of vaporization. And so this is not true as we get farther and farther from the triple point. Couple of definitions here. The standard boiling point is the temperature at which the vapor pressure of the solution is equal to 1 bar. Remember, boiling point is the temperature at which the vapor pressure of the liquid or the solution is equal to the pressure above it. Usually it's atmospheric pressure. A normal boiling point, this is the one we usually talk about in Gen Chem, is the temperature at which the vapor pressure of the solution is equal to 1 atmosphere. Slightly different than 1 bar, so these are different temperatures. So that's a pressure temperature phase diagram. If we make a graph of the temperature of the substance versus the amount of thermal energy that's been transferred into it, Q sub P, the constant pressure, we get a curve like this. So we start out with a solid at some temperature down here, but beneath its melting point. As we add thermal energy, the temperature of the solid increases. We can calculate that using the heat capacity of the solid. Then once we get to the melting point, the temperature stays the same during the period in which the substance melts. And here we have liquid and solid. At this end, we have more solid than liquid. Here we have more liquid than solid. But the temperature stays the same, and we can calculate the amount of energy required to do that using the heat of fusion. Once we've added enough energy to melt the solid at that temperature, this is whatever its melting point is, this temperature. As we add more thermal energy, the temperature of the liquid starts rising, and we can calculate that using the heat capacity of the liquid. Once we reach the liquid's boiling point right here, once more the temperature stays the same as we pour more energy in, and the liquid vaporizes to become a gas until all of it has been vaporized. And then if we keep putting energy in, the temperature of the gas rises. Here we can calculate the amount of energy required using the heat of vaporization. And once we're here, we use the heat capacity of the gas. Remember, the heat capacity of the solid is different than that of the liquid, which is different than that of the gas. During sublimation, going directly from the solid to the gas, it looks just like this. Heat up the solid, we get to the temperature of vaporization, and same idea, the temperature stays the same until it becomes a gas. So the pressure temperature phase diagrams are not all simple. For instance, this is a phase diagram for water where it takes into account the many different phases that the solid can have. So a solid can have more than one phase. Here there's 11, I think, different phases, structures of ice. And this is, by the way, this is a logarithmic scale because we're talking 1,000,000 pascals up here. So this is, not in the same, it's logarithmic where this is just linear on the bottom for temperature. But, the point here is that you can have more than one type of solid phase. And there's a triple point, everywhere there's multiple triple points here. So that would be a triple point, that would be a triple point, that would be a triple point, that would be a triple point. That's a triple point there, and so on. And at these triple points here, the different solids are in equilibrium with each other, solid phases. Just for an example of how that can be, this is ice 1, normal ice down here. It's hexagonal. If you look at the crystal structure, under most conditions we deal with that's the stable form of ice. And we know that it's less dense than water, at least until the water gets up above about 4 Celsius or so. This is ice 6, more compact. Its density is like 1.31 grams per milliliter. So pressure temperature diagrams, can look quite different. This is the one for sulfur. Has more than one triple point. Different solids. This is the crystal structure, monoclinic versus rhombic. The liquid and the gas phase. This is a normal, carbon dioxide phase diagram. This is 1 atmosphere, so normal room atmospheric conditions. We see that as we increase the temperature from negative 140 Celsius or so, at 1 atmosphere it goes directly to the gas phase. That's why it's called dry ice, because when you put solid carbon dioxide out on the countertop or whatever, it sublimes, goes directly to the gas phase. You never see the liquid form. So Gibbs, William Gibbs, came up with the phase rule. And here it's pretty simple, but here's how it goes. We're going to use this later on. So in a single phase region, so where it's just solid, or it's just liquid, or it's just gas, there's 2 degrees of freedom. The degrees of freedom are how many independent variables there are needed to describe the system. So temperature and pressure are independent in a single phase region, 2 degrees of freedom. Along a coexistence line where the 2 phases are in equilibrium, we have an additional restraint. That is that the chemical potential, let's say there's 2 phases, alpha and beta. The chemical potential of the alpha phase must be equal to the chemical potential of the beta phase along that line. So that's a relationship between temperature and pressure that's involved here. So that takes away 1 degree of freedom, and there's only 1 degree of freedom left along a coexistence line. Now, following that through, at a triple point, there's 3 phases in equilibrium. So we have the chemical potentials all have to be equal to each other. That's an additional constraint, and there ends up being 0 degrees of freedom at a triple point. And so that's where Gibbs has his phase rule, that the number F is the number of degrees of freedom, like 0, 1, 2, or 3, is equal to just 3 minus P, which is the number of phases. So in a single phase region, 2 degrees of freedom is equal to 3 minus 1 phase. And he shows later that the degrees of freedom can never be negative. So that means that what that ends up showing is that the most number of phases that there can be in equilibrium with each other is 3.